You know I like stuff on the internet. Here is a great video. I really enjoyed it, even though it does have some problems, and I don't know why they did it. Peyton Manning throwing a football off of a building. I'm just going to show you a little part of this because this is what we want to model. We want to model how you would throw a ball off of a building like this. And here's the, they're going to throw it off this one particular building. I can't remember the name of it. And they want it to go into this park and have someone catch it. And there's a whole bunch of great physics questions here. So I want to do two things. I want to look at the range as a function of launch angle without air resistance, and then do it with air resistance. And that's what we're going to do in Python. So we know a couple things from this building, from this video. I'm going to assume an initial velocity. I'm going to assume the height of the building, and let's get to it. Okay, stop that. Let's jump over to the paper, and I want to derive the real range equation. Okay, so the real range equation. Here is the fake range equation. If you look up range equation, you'll see this. Or one that has a 2 theta in there and sine of 2 theta, it doesn't really matter. But this is bad, right? I hate this equation because people think this is the range equation and it'll give you the range no matter what. But this only works for the case where you launch and it lands at the same vertical height. But what if it doesn't? That's what we're going to do. So let's say that it launches at some height h, like from the top of a building, some angle theta, so that's h, this is v0, and it's going to go pew. So over here, you know the maximum angle, what do you want to maximize cosine theta, sine theta, is when they're both cosine of 45, sine of 45. That's going to give you the greatest term right there. You can see a little bit better when you put it into sine of 2 theta, but nonetheless, I like this version better. Doesn't use any tricks. But what about over here? What angle should you throw it at to get the maximum range? Is it 45? And the answer is no, it's not 45. Okay, but let's just do it. For projectile motion, we can break this into an x motion and a y motion. And the key here is that the x motion and the y motion are independent. So at this point in the trajectory, it only has a downward gravitational force. That means in the x direction, the velocity is constant. So I can say Vx0 is V0 cosine theta. So this is 0. So the initial velocity times the cosine theta is the x velocity. And with that, I only get one equation. It looks like this. X equals x initial plus Vx initial t. So this is assuming that t equals 0. It's at x equals 0. x0. Yeah. And this would be my final position x. And this is my initial position x0. And we want to find that. I know this. I'll assume that's 0, but I don't know the time. So now let's go over to the y equation. In the y equation, I do have an acceleration. So I have y is initial y plus the initial y velocity times t minus 1/2 g t squared. Since it has a gravitational force of mg, the acceleration is going to be g in the negative y direction. So that's why it's negative g. And it's just a kinematic equation. So in this problem, I can actually put in some values. I can also say Vy0 is equal to V0 sine of theta. And then I can say that the final position, let's call this my origin, then the final y position 0, the initial y position's h. So let's put that in, 0 equals h. I'm just going to call this Vy0 for right now. We'll substitute this in later, plus Vy0t minus 1/2 g t squared. And I want to solve for t and put it in up here. That's all I'm doing. Well, you can't do that, right? Even if I know the number for h, even if I know the number for v0, which I do have some estimates for, I'll put that in my value. Actually, I'm going to say v0 is, what did I get, 27 meters per second. I got that from looking up the approximately long distance speed for an NFL player, and then h was 88 meters. I measured that. And if you want all the details, I'll put a link to my blog post about this if you want to read it. So I know h, I know v0. I don't know theta though, because I haven't figured that out yet. But I can't solve this, right? Because I have a constant, I have a t term, and I have a t squared term. That says I have to use the quadratic equation. So in general, you see it looks like this. x squared plus bx plus c equals 0, then x is going to be negative b plus or minus the square root of b squared minus 4ac over 2a. So in this case, we have t instead of x, and we have these. Our a is going to be negative 1/2 g, b is v0, y0, and c is h. So let's just put that in. T is going to be negative b, that's b, negative vy0 plus or minus the square root of that squared, vy0 squared, minus 4 times a, so that's going to be negative 2g minus negative 2g times h. So it's going to be plus 2gh. I did that right? So 4 times this is negative 4, negative 2g, and then that c is h. Yeah, okay. And then I need to divide by 2a, which is going to be negative g. And we're going to get two terms. We're going to get a plus and a minus. So let's just go ahead. I'm going to get rid of this. I'm going to multiply top and bottom by a negative sign, and that becomes minus plus, but I'm going to write it as plus minus, right? So that flipped. I had to flip that too. So I'm actually going to get two terms here. I'm going to get v0 plus this term over g and v0 minus this over g. And the one we're going to want the plus because these two terms correspond to the parabolic solution to when the ball was at y equals 0, which is, there's two, right? You can go back in time to get that one, and that's going to be that minus sign. It'll give you a negative value. And the plus will give me the forward time one. Okay, so that's my t. Now I can take that and I can plug it into my equation over here, and I get, let's say x0 equals 0. So x final is vx0 times vy0 plus the square root of vy0 squared plus 2g, and g is 9.8. We've already taken into account the negative h, all of that over g. Now I want to plug in my expression for vy0 and vx0, just because. So I get x equals v0 cosine theta times v0 sine theta plus the square root of v0 squared sine squared theta plus 2gh, all of that over g. And that's my range. So what I want to do is to take my values for my initial velocity and my height and just change this is kind of complicated to see the answer, right? But I want to change the value of theta and make a plot of range as a function of, so it's going to be x as a function of theta, like that. And then so we can see which angle gives us the maximum range. And then we're going to repeat the whole thing with air resistance, which is way more fun. But this is a good warm-up exercise. Okay, so all I need to do is to calculate this for different values of theta, jumping over to Python. Let's do it. Oh, that's still Peyton Manning. Okay. I put some values in here. I put in the initial velocity. I put in the height because I didn't want to forget it. And then I put in my initial theta and then how much my theta is going to change. It doesn't really matter. I do need a graph. G1 equals, I will give you the code down below. You know I'm going to give you the code. Graph title equals, let's say, real range. And that's just being mean. But, you know, whatever. X title is going to be equal to angle. And let's just do it in degrees. I think in degrees. And then the Y title is going to be equal to, let's just call it X in meters, how far it goes in the X direction. And then let's put a width of 400, height of 200, just so it makes a nice graph. Now I do need a graph to plot. F1 equals G curve. I can't type sometimes. Color equals color.blue. Okay, so now I have my equation. I could make it a function, but I'm not going to. So what I want to do is to put in theta is equal to 0 and then launch the whole thing. Okay, and then get the final x position. And then do it again, but that equation tells me the whole answer. So I just need to calculate x with that theta and then change theta and do it again. So I'm going to go from 0 to 90 degrees, pi over 2. Why? And that theta, d theta, I'm thinking of this in terms of, is that going to be my, should I call that, I'm going to leave that in radians. Yeah, it's radians. So while theta is less than pi over 2. So number 1, calculate x. So I'm going to use my range equation that I just calculated. X equals, I'm typing in, I'm looking at it, v0, parentheses, v0 times cosine theta times v0 times sine theta plus the square root of v0 squared times sine theta squared plus 2 times g times h. And then that's the square root, that's that, and that one then divide by g. It should be right. Let's just, oh, you can't even see that. Look at that. Sorry about that. There. Well, it ran on. You knew what it was. So now I'm going to plot that. F1.plot. On the horizontal axis, it's going to be theta. Theta times 180 over pi. I'm converting that back to degrees, like degrees. And then on the horizontal, it's going to be x. Now I'm going to increase my value of theta. Theta equals theta plus d theta. And that should work, but you just never know. Okay, there you go. So that's my range as a function of launch angle. And you'll notice that I get a maximum range right here at 29.6 degrees. Now, let's just check, right? There's a really great thing that we can do to check our code. And that's to say, what if the height of the building is 0? Then I know the maximum angle should be at 45. Well, that's easy to check, right? I can check that. So let's go back over here. Let's save this thing. This is an easy program, right? So let's just make this 0. I like to do times 0 so I don't actually delete it, but it is 0. And I run it again. And there you go. Max range at 45. That's a win right there, people. That's a win. Okay, so if you don't have air resistance, from that I can find out how far it goes and what angle it should be thrown at. And the maximum angle depends on how high you're throwing it from. Okay, so you can play around with that. You can get all these graphs and so forth. So now what if I want to find the max range with air resistance? That's pretty tough. Let's jump back over to the paper and talk about range with air resistance. Suppose I throw a football. Here's my same picture. Now I'm going to draw it as a ball. And it goes through the air like this. At some point right here, it has two forces acting on it. It has the downward gravitational force, mg, and then it has a backwards pushing air resistance force, F air. This makes it very difficult to model because the air resistance depends on the speed of the ball. We can model the air resistance of a ball with the following. F air is negative 1/2 rho a c magnitude of the velocity squared times the velocity unit vector. So in this case, negative is negative and 1/2 is 1/2. Rho is the density of air. I'm not going to write it down. A is the cross-sectional area of the object. C is a drag coefficient that depends on the shape. That's the magnitude of the velocity, and that's a unit vector in the direction of the velocity. So if it's moving in this direction, the velocity vector is always in the opposite direction. This is why it's really difficult, right? Because since it's a vector in the opposite direction, the x component of the velocity depends on the y component of the velocity, and the y component of the velocity depends on the x. They're intertwined because of the square, because there's this magnitude here. So you can't separate them. And that makes it an impossible problem to solve. I think it's impossible. If you had linear velocity, it would work. If you move in one just up and down, you can solve it. But in this case, you can't. What do you do when you can't solve an unsolvable problem? You cheat, right? Of course you cheat. So what we're going to do is to use a numerical calculation. So let's pick a time step of 0.01 seconds. During that time interval, I'm going to assume that the velocity doesn't change very much. And if the velocity doesn't change very much, then I can assume that the air resistance force is constant over this 0.01 second time interval. So I can say that the net force is the rate of change of momentum. If you want to write this in terms of mass and acceleration, you can. I always do it in terms of momentum, so I'm kind of stuck. That's just what I do, where momentum is mass times velocity. You could do it as mass times the change in velocity. It will work. Okay. So, but if this is the case, I can calculate this vector value of the net force, and I can relate that to the rate of change of momentum like this, such that F net is P2 minus P1 over delta t. So if I calculate this force, if I calculate that force, I know the change in momentum, and I can find the final momentum. I get P2 equals P1 plus F net delta t. So if I know the momentum at the beginning of the time interval, calculate the force, the net force, I can find the new momentum. Now, and that's kind of a big deal. Now, I can assume that it's moving at a constant velocity, which it's not, and to say that V average is the change in position with respect to time, which would be R2 minus R1 over delta t. So this is the position at the beginning of the time interval. This is the position at the end of the time interval. Well, and the velocity is mass over the momentum over mass. So I get R2 equals R1 plus P over m delta t. And that's it. So I'm going to do the following. Calculate the net force. Update the momentum. Update the position. Update time. And then do it again. And that's one way to model the motion of a ball. Now, I do need to know the density of air, the cross-sectional area of the ball, the drag coefficient of the ball, the mass of the ball, because it's in there too. The mass doesn't cancel now, but then I can do all this stuff. So let's do this in Python. Let's just do one trajectory to make sure it's working, and then we will change the initial launch angle and find out where it lands, and it's going to be great. So it's a little bit more complicated program because I don't have just one equation. I have to do a loop in order to find each thing, but let's do it. Switching back to Python. And here is my second program. So in the second program, I've already put in some stuff, as you can see. I have G, which I'm going to change to the vector value of G. Let's change that to a vector. Vector 0, negative 9.8, 0. Because that way I want to do stuff with vectors. And then V0, that's my launch velocity. H is my height still. Theta is fine. The mass in kilograms, that's the mass of a football. This is the circumference of the football. I looked it up and said circumference, so that's fine. So I wanted to find the radius, and then I didn't call it R because I'm going to use it for something else. And then the cross-sectional area, it looks like a circle. And then the drag coefficient, I looked up, someone did the drag coefficient for a spinning football. And that's kind of a big deal later, and we'll talk about homework questions on that later. So let's just make a graph of the trajectory. And I'm not going to give it a title, but let's just, for now, call it X title equals X versus Y, right? So that's trajectory. And then I do need to get the width. 400, height 200, and I need a graph to thing. F1 equals G curve. Color equals color dot blue. Okay. So I have all this stuff. I need to start off with the initial position, initial momentum of my ball. So let's do that. T equals 0. dt equals 0.01. That's what I said. You can make that smaller if you want. Now the initial momentum, I'm just going to call P. So P equals m times V0 times vector cosine theta sine theta 0. So this is really a useful thing to create these as vector quantities and use vector quantities so we don't have to deal with the x and y direction. We'll just say p, and it has x and y and z, even though you don't need that. So this is the x component of the velocity if I know the angle. This is the y component if I know the angle, and then mass times velocity. Now for the position, I'm going to call that r. R equals vector 0, h, 0. So it's going to start 0 in the x direction, h in the y direction, 0 in the z direction. I think I'm ready. No, I have, did I put rho? I didn't put rho. A, C, okay, rho equals 1.2. That's the density of air. How did I not put that in there? It's weird. Rho, A, C. I got it. So let's do this loop. I'll say while r dot y is greater than 0, right? So while it's above the ground. Number 1, calculate the force. F net equals m times g. It's not negative, right? Because g is a vector. Minus 0.5 times rho times a times c times the magnitude of the velocity. Okay. So I'm going to write this as mag p divided by m, right? So I need the velocity, and then I need to square that. And then I need to multiply it by a unit vector, norm p. So I don't need to multiply the unit vector of the velocity because it's a unit vector. So I'm dividing by the magnitude anyway. So I can do p or v, so that should be fine. And I'll show you one way we can check it a little bit. Okay, so now I know that net force, I can update my momentum. P equals P plus F net times dt. I can update my position. R equals R plus P times dt over m. Update time. T equals T plus dt. And now I'm going to plot it. F1 dot plot r dot x, r dot y. So that's the x component of the position and the y component of the position. And that should work. Okay, I think it did work. I mean, you can't necessarily see that it worked, except let's do one thing. Let's just try something, okay? So this, I threw it straight off. That makes sense. And it went a distance of 106 meters. Now, if I turn the air resistance off, it should go farther, right? So let's test that. And that'll be a good little test. So I can turn off the air resistance by changing this drag coefficient to 0. So now there's no drag coefficient, so the force is 0 no matter what. It should go more than 106 meters. And it went not too much further, 114. That's kind of strange, kind of surprised with that, to tell you the truth. Huh. Is my drag coefficient too small, I wonder? Well, it doesn't matter. You can change that. It's all about the idea here. It's not about the actual answer, surprisingly. Okay. So now we can make a graph of the range as a function of theta. So over here, let's put this as theta in degrees. And this is going to be x in meters. That's all fine right there. Now all I'm going to do is to take this loop and put it in a loop. So I'm going to say while theta is less than pi over 2. And then I'm going to do all of this stuff right here in the loop. So I'm going to indent it. Now at the beginning of the loop, I need to do something important. I need to reset the momentum and reset the position. So r equals vector 0, h 0, t equals 0. I need to reset the time. Otherwise, it's going to use the time from before. And then I need to reset the velocity and the momentum. So p equals v0 times m times vector cosine theta sine theta 0. I think that's it. Yeah. Now, once I'm done with my loop here, I want to plot theta times 180 over pi, and the final value of x, which is just x. No, it's r dot x. R dot x. Now I need to increase my value of theta, or my loop will run forever. Theta equals theta plus d theta. Okay, and I need to, oh, yeah, let's turn that back off. And there we go. Okay, so remember I had 29.4 was my maximum angle. Here it's 28, so it's different. It's not that much different. Kind of surprised. Let's turn the drag coefficient up, make it bigger just for fun. Because let's put this at 1. I feel like that's wrong. I'm gonna Google that in just a second. So now I have a maximum. It's much smaller. Okay, that makes sense. And it doesn't go as far either. So it seems to be working. Let's just real quick try something. Drag coefficient football. They use 0.18 to 0.2. Okay, well let's use 0.2. That's fine because I thought it was too small anyway. So 0.2. And that looks a little bit better. Now, for some homework. And I'm just going to tell you some homework questions here. If you watch that video, there's some really interesting things to look at. You know, can you measure the time of flight from the video when Peyton throws the ball and use that to kind of go backwards and find out what angle he threw it at or what drag coefficient it is? Try to see if you can make a model that matches that data. That's really the coolest part. You might be able to actually estimate the launch speed and angle by looking at the close-up video of him throwing it. You could do a video analysis and do that. What about when someone catches the ball, right? Chris Carter was catching the ball down in the park, and he said his hands really hurt. How fast was the ball going? What kind of impact forces would he have to catch it over a distance of probably 0.7 meters? But you could try to estimate that, maybe even measure it with the video analysis. That'd be kind of fun. What about when the ball goes out of a spin? So if you look at the video, it starts off with a spiral, but then it goes into a flat spin, and that's going to change the drag coefficient dramatically for that ball. It'd be kind of fun to do that in some way. I'm not even sure how you do that, but it'd be kind of fun. Okay, so there's a bunch of fun things you can do with this kind of problem, but mostly I wanted to talk about modeling the range of a ball with air resistance. Code for both of these programs down below. Link to my blog post where I did analysis of this is also down below, and that's that. I'll talk to you guys later.